Okay, so that should be recording now. So what we're going to look at is we're going to look at lossy and lossless compression. But the other thing that you didn't do in your AS is you didn't look at encryption or hashing. So we need to talk a little bit about that today. Now, just as a recap, you need to remember that lossy is a compression format that removes the data. So remember, you can't get it back to its original format. But what I want us to get out of today's lesson is I want us to be able to look at lossy and lossless, run length encoding, so that's something new that will also be added to the curriculum, symmetric and asymmetric encryption, and different uses of hashing. Okay. Now what we've got here is lossy. Now the way that lossy compression works is it works by actually removing data from the file. So if I have an image where I've got the same pixel over and over and over, I could remove that and kind of repeat other pixels. Or if I had a song, what it does is it works by actually removing data from it. Now the drawback of that is if you use lossy compression, you can never get back to where you originally were. So if I had an MP3, you can't get it back into its purest format. It's not like you can go back to analog, okay? Yep, so you also need to acknowledge in your exam questions that you can lose the quality of the image or quality of the video or quality of the picture. You always need to acknowledge that. That's the drawback of that. And also, if you've got any questions while I'm doing this, feel free to ask. Yes? Right, so with some images, it can be noticeable to the human eye. It can be, but the idea is that lossy, you usually remove the data until it's noticeable. Does that make a bit more sense? All right. So lossy is generally used in images, sound, and sound files, and it's used where human perception may not spot the quality. So that's what I'm trying to get at there. So I will take it back. If you remember the image on the beginning of the slide, I will take it back as far to the point where you start to notice it. All right. Now, the big idea of using that is particularly if you've got like an it wouldn't be an MP3 file, it might be a WAV file in its purest format, and that might take up 40 meg. And the need for this is so that if you wanted to upload your images or upload your videos or songs and that, you can put it on the cloud, you can upload it anywhere into a space without it needing to take up so much space, okay? That's a good point to acknowledge there. You're going to economize storage space. That's usually worth a mark in an exam, actually acknowledging that the reason for it is to actually give you extra space. Remember what we were talking about where you've got your knowledge, your application, your evaluation. This would be showing your knowledge and your application because you're acknowledging that the file size goes down and you're going to get more space because of it. JPEG images are usually used. Now, that is an example of digital sampling. So what would happen there usually is this is your sound wave. Now the way that sampling works is say high frequencies that are not noticeable to our ear. So you know, like things like dogs might hear, those sounds are removed so that it isn't noticeable with the quality. So that's what's happening there. So it's sampled at key points and then you get your sound. But what can happen is if the sample rate is bigger, you get a closer sound to the original analog sound. If you have less samples, because you imagine these are wider apart, that's more sound that's going to be cut out, so it's going to have an impact. There have been GCSE questions in the past where they've asked you about the impact of sampling. So you need to be able to acknowledge that if you have less samples, that's less times you've actually looked at the original sound, so you're going to have worse quality and you're not going to have as big a file. You need to be able to acknowledge that. So lossy works for sounds. Sound files are sampled at key points. Data is removed at high frequency. That's what I was getting at with dogs. Videos are compressed using this method, and some of the formats are JPEG, MPEG, and MP3. Do not forget those because they sometimes give you like tick box questions in your exam. They're your easy marks. You don't want to lose those. Then you've got lossless. The idea of lossless is that it will reduce the file without taking out any of the data. And there's some methods that you need to know about, such as dictionaries, I'll talk about in a minute. It's basically, if I had your Word document, I would actually, say for example, the word the is used 10 times. I would allocate that like number 1. and say the letter A was used 20 times, I would allocate that as number 2. And the idea is that you have this dictionary of all the possible words and you just put the numbers in, and it can rebuild the original file. So you can always get back to the original when you use lossless. Yes?
So kind of like procedures and functions? Is that what I mean?
Yes, so procedures and functions, any programming, you would always use a lossless compression format. And the reason for that is basically to do with hazard and danger. Because, for example, if you worked in a factory, a nuclear plant, and you wanted to send an update of the newest program, and you used Lossy and bits of data happen to go missing, and you run that, you're going to end up with a nuclear meltdown. So it's really important. So that's what it's talking about, multiple data being used. So here's an example of dictionary coding. So if you are asked what dictionary coding is in the exam, so what I've got here is, ask not what your country can do for you. But, so that's my dictionary. I've only got 9 words in it. But actually, the thing that I make back up says, ask not what your country can do for you, ask what you can do for your country. That's actually what that says, and it can rebuild that because it's got those words in that dictionary. So that is what dictionary coding is used for in lossless. So in A-Level, you obviously in AS you just had to know the difference between the two. At A-Level, they're probably going to ask you to give an example, or they might show you an example and ask you to say what that is. So that's dictionary. Making sense? All right. And it will, like I said, you can restructure and re-get back the original. The dictionary must be stored with the message, because if I haven't got a dictionary, I can't remake the file. All right. There are other ways which I will expect you to research in a moment, but there is the LZW algorithm that is used for generating the dictionary as it goes along. So as it compresses, it makes the dictionary. That's basically what it's saying. So when a sequence is found that is already in the dictionary, the next character is examined, and if it is new, it is added to the dictionary. So it keeps looking at sequences, and if there's something new that it hasn't seen yet, it adds it to the dictionary. You can research this and look into it a bit more. I'm going to pronounce this probably wrong, but it's Zempor-Ziv-Welch. But that's one technique of building the dictionary. So formats you have are zip, GIF, or GIF as some people say, and PNG. Right. Run length encoding. So this will be used with things such as images. Right, so run length encoding is basically, if you have a bitmap image, you might have a row of pixels that are all the same shade of blue. So what you can do is allocate that as B100, and all of those pixels are basically repeated. Now, the image can be made exactly the same. It's not as good as lossless. Now, the reason for that is, I mean, if you've looked at BMP files before, have you noticed the file size is a lot higher? Yeah? But lossless is used for reducing file sizes, but it's obviously not very useful for all things. Computer programs, it always needs to be used, though, because of the danger and the risks of breaking, like, nuclear plants and so on. So run length coding is basically, it will allocate in an image a whole load of bits, and it will repeat that. I'll go back over this, don't worry. Now, encryption. You may have heard of encryption before. Where? Give you a hint. What did you say? Anywhere? Security. Who? Has anybody seen the movie that was all about it? Movie all about it. There's a famous guy in the war. Pardon? The Enigma machine, right? So we had encryption. Well, we didn't have the encryption. The Germans had the encryption with the Enigma code, but the British, we had Alan Turing, who was an amazing guy. He went and he basically, with his team, found out what the Germans were doing and was able to decipher their messages, because that's how Germany was so clever in the war, because they were sending secret messages through Morse code, And we were getting that Morse code, but we couldn't figure out what it said because it was encrypted. There was an encryption key. Now, we use encryption to stop data from falling into people's hands. So, for example, if I had your personal information on my laptop, I would need to make sure that it's encrypted when I take my laptop out of the school, because I'm responsible for holding your personal information. And if that gets into somebody's hand, which act is that breaking? Data Protection Act. Well done. So you don't want your personal information getting in the public domain. And what that means by the risk, these days we have a risk of people eavesdropping, is people basically seeing your personal information and looking over your shoulder. That's kind of what it's getting at. So lots of people have had to actually adjust the way that they behave online. I mean, on your Facebook accounts, on your Twitter accounts, you don't send out your phone number. You lock it down. You lock your profile down so that future employers can't see you. You do that sort of thing. All right? And that's why we need encryption. Now, we will use it for things like trade secrets. It might be that the government use it. I mean, you use encryption every day, believe it or not. You've got an app on your phone that you use, beginning with a W, probably, a lot of you. WhatsApp? Yeah, WhatsApp encrypts the messages. And there was a reason why the government actually wanted to get rid of that, because they weren't liking people were using it for other things. So the government were actually going to block and ban WhatsApp in this country at one point, because your messages are actually encrypted to each other. All right? Personal data, if I needed to send somebody a credit card number, I might do it through encryption. I wouldn't bother doing it at all, to be fair. So where security is vital. Most people have used encryption, but I'm going to show you a video in a moment that talks about the Caesar shift. Now, back in the day, we'll say, Julius Caesar used an encryption method called the Caesar shift. Now, this encryption method is actually pretty easy to crack, and it's what we call a symmetric cracking system, because both people have the key and they can actually unlock it. So I'm going to show you a video. If you watch that, you'll see an example of what symmetric encryption is like.
The first well-known cipher, a substitution cipher, was used by Julius Caesar around 58 BC. It is now referred to as the Caesar cipher. Caesar shifted each letter in his military commands in order to make them appear meaningless should the enemy intercept it. Imagine Alice and Bob decided to communicate using the Caesar cipher. First, they would need to agree in advance on a shift to use, say 3. So to encrypt her message, Alice would need to apply a shift of 3 to each letter in her original message. So A becomes D, B becomes E, C becomes F, and so on. This unreadable or encrypted message is then sent to Bob openly. Then Bob simply subtracts the shift of 3 from each letter in order to read the original message. Incredibly, this basic cipher was used by military leaders for hundreds of years after Caesar.
I have fought and won, but I haven't conquered over man's spirit, which is indomitable.
However, a lock is only as strong as its weakest point. A lock breaker may look for mechanical flaws, or failing that, extract information in order to narrow down the correct combination. The process of lock breaking and code breaking are very similar. The weakness of the Caesar cipher was published 800 years later by an Arab mathematician named Al-Kindi. He broke the Caesar cipher by using a clue based on an important property of the language a message is written in. If you scan text from any book and count the frequency of each letter, you will find a fairly consistent pattern. For example, these are the letter frequencies of English. This can be thought of as a fingerprint of English. We leave this fingerprint when we communicate without realizing it. This clue is one of the most valuable tools for a code breaker. To break this cipher, they count up the frequencies of each letter in the encrypted text and check how far the fingerprint has shifted. For example, if H is the most popular letter in the encrypted message instead of E, then the shift was likely 3. So they reversed the shift in order to reveal the original message. This is called frequency analysis, and it was a blow to the security of the Caesar cipher.
So there are two different types of encryption. As you can see here on this slide, is you've got symmetric. Symmetric is when both parties have the key to get it back. So I would use an encryption key, say with the Caesar shift of 3, that moves it forward 3. Then the person receiving the message knows that they need to go back 3. So that is symmetric. Think about it. Symmetry, 2, the same, all right? So that key is used to encrypt and decrypt the message. The sender will receive it. It could be 1 byte at a time, or it could be the whole piece of information. And that key can be used multiple times. It might be used for just a single letter, or it might be a whole chunk of text, or it might be a paragraph. But the idea is that both parties have the same key. Now, the second type you've got is asymmetric, where one party will have one key, but you will have but say, for example, Brandon might have the other key. All right? So there needs to be 2 different keys, and what happens is I would use one key to encrypt the message and then would need another one to decrypt it. So one of those keys is publicly known, everybody gets to see it. The other one, nobody gets to see. So it uses a private key to decrypt it, which you can see the blue, and then you've got a public key which everybody gets to see. Now, it does use a lot more processing power. So if you are asked in your exam about the drawbacks of that, you'd need to say, well, by using this, it's going to use a lot more of my processing speed. Yeah.
So basically everyone can see the encrypted version of the message.
Everybody's allowed to see the encrypted message, all right? But only that person has the secret key that matches that public key. And I'm going to give you an example of that in a moment. So one example is hashing, all right? Now, if you want to quickly write and read files, you can use something called hashing. Now, an example of this is in a database, your key field might be used and changed into a disk address somewhere on your hard drive, basically. Now, I'm going to show you an example of it to make a bit more sense, but it allows the disk to go to a specific part. So this isn't necessarily just talking about encryption here, it's used within the computer system as well. So what hashing would do, say for example you've got the number 2563546. It takes the last 3 numbers and then it will allocate a disk address of those numbers. So you know how I've got the last 4 numbers as 546. That's now the disk address, the location on the disk. Now that is accessed, and then that record, so the whole account number, is placed there. So this whole account number is placed in that disk location, all right? Now, if there is something already there, what it does is it will go to 547 and place it there instead. Now, that is moved to the next location, but again, if it's full, then they have a special area for data collisions where that's been filled up. So there's a special area allocated so that that doesn't happen and you don't end up with your programs or your data going missing. Now, hashing algorithms, they tend to be used for passwords. Now, the reason for that is because, say for example, I create my user account. I'll create that password, but what happens is the password isn't stored on the network or any server. The hashing is. All right, now that sounds a bit weird, but when I create my password, the hashing algorithm will generate the hash code. All right, now, rather than needing a decryption key again, what happens, this is like a one-way system. Hashing is one way. When I type in my password, that algorithm is applied to that data again, and then the hash codes are just compared to get you logged into your system. So that way, my password isn't seen by anybody. Am I making sense to people with this? I will go over it again. So I've got a password of Ray. Now, rather than storing that somewhere that isn't secure, like storing the word Ray on a server, what happens is the hashing algorithm will generate that hash code, and that will be stored somewhere. Now, when I log into the computer, the hashing algorithm works again and generates the hash code based on what I've typed in as my password. That hash code is then compared with the hash code that was there. That way, nobody ever sees your password. It's only the algorithm that has interpreted that. I hope that makes sense. I'll go over it again on the board in a minute. And that's called one-way encryption, because that way I don't need an encryption key. It's just the algorithm that's doing all of the working. So when you choose a password, it uses the hashing algorithm to give a hash value. The password isn't stored on the server. We've said that. When the user logs on, it's applied again, and you're given hash values. Now, this method is probably one of the most secure. You are able to crack it, but it's difficult because you've got something called brute force. Has any of you heard of brute force before? Yeah. Right, now what do you know about brute force?
It's like, for example, with an actual lock, when you actually try to smash it instead of lock picking it.
Yeah.
So you actually people after actually know that you block into it.
Yeah, so you keep trying, basically. So brute force, like you said, smashing the lock, that's pretty much what you're doing. You are trying everything until you get that password. So say, for example, you have a dictionary of every word known to mankind. Somebody on this planet is bound to have their password as their favorite football team or their favorite dog or their favorite band, and those things are in a dictionary, and that is then checked, and the brute force keeps going. Did this password work? No. Did this password work? No. That's what brute force is. It keeps trying it. All right. So you can make it even more secure by using hashing, but there's something called salt that you can add to it. All right. So what salt is it adds a random string to the end of it, so it complicates it even more. So this makes the hash value different to the same password, but like with the dictionary, you have to have the salt word stored somewhere. All right, so you've got your password, right, and you add the salt value on the end. So I've typed in Ray, but then there's also, as part of the encryption algorithm, a salt value added to that. Now, rather than storing the hash value is stored somewhere, and the salt value is stored somewhere. So that's like 2 levels of encryption on it when it compares it in the algorithm. Yeah? So it's like a second level, if you like. So that's the salt. If you want to do some more research around that to understand that, I would recommend that.